Thank you everyone for checking out this talk. Today we're discussing improved inapproximability results for VC dimension and Littlestone's dimension. Let's start by reviewing a few important definitions. Given a domain X, a concept is simply a Boolean function on the domain X, and a concept class is just a set of concepts. Throughout this work, we consider a concept class as being represented explicitly as a Boolean metric, where the number of columns is equal to the domain size, and the number of rows is equal to the number of concepts, denoted by M here. An example of concept class is that of threshold. Here the domain X consists of real numbers, and each concept has a threshold, denoted by I here, such that the concept evaluates on X to 1 even only if X is no smaller than the threshold. For example, if our domain X is 1, 2, 3, then we could have 4 concepts here, where the first concept is all 1 and so on and so forth. Next, let's recall the definition of VC dimension. And for that, we have to start with shattering. We say that a subset S of the domain X is shattered if, when we restrict the concept class on just this subset S, then it contains all the 2 to the size of S distinct functions on S. Just to give you an example here, if we look at the threshold on the right here and we restrict on the set where S is just 1, then this set is shattered because both 1 and 0 occurs. But if we look at the set that is 1 and 2, it is not shattered because 1, 0 doesn't occur in the restriction. The VC dimension is then defined as the maximum size of shattered set. In the case of threshold, the VC dimension is just 1. Now, the importance of VC dimension is that it determines the sample complexity in the probably approximately correct packed learning model up to a constant factor. Since we will not be using the packed model directly here, we will skip the definition for brevity. Next, let us consider the second dimension in the title of this talk, the Littlestone's dimension. And while there is a combinatorial definition of the Littlestone dimension, we will not use it in this talk, so we will instead use the definition based on online learning. So the setting of online learning is as follows. It runs in iterations, and in each iteration I, the algorithm receives some xi in the domain X. Upon receiving this xi, the algorithm has to predict y tilde I. After this prediction, the algorithm then gets to see the true label yi. The goal of the online learning algorithm is to make as few mistakes in the predictions as possible. The guarantee that we have is that all the xi and the true label yi are all consistent with some unknown concept in the class C. The Littlestone dimension is then the optimal mistake bound among the best online learner with respect to worst possible sequences. Now, there is one important online learning algorithm that is generic and we'll be using later. So let me state that here. This is the so-called halving algorithm. So the algorithm works as follows. We keep a candidate set of concepts that so far agree with all the examples xi, yi that we have seen. Whenever we receive a new xi, we consider the 2 possible predictions 0 and 1. These 2 possible predictions partition the class of candidate into 2 sets based on whether the true value is 0 or 1. Then we predict the one that agree with at least half of the candidates. What this means is that each time we make a mistake, we rule out at least half of the candidate concepts. And this means that the mistake bound that we get is at most log of the size of the concept. And this also implies that the Littlestone dimension of any concept class is at most the log of the size of the concept class. Although, of course, in some cases, there are smarter algorithms and the Littlestone dimension can be much smaller. All right, so with those definitions in mind, let's state the computational questions that we are interested in here. The questions are as simple as it gets. We are given a concept class C as explicitly as an m times x metric, and we want to compute its VC dimension or its Littlestone dimension. Here we will use little n to denote the size of the input, which is as m times x. Now there are a few useful observations. As I stated earlier in the previous slide, the Littlestone dimension is at most log of m, where m is the size of the concept class. And it's also not hard to verify that the VC dimension is no more than the Littlestone dimension. So what this means is that we can actually use a certain brute force algorithm to compute the Littlestone dimension and the VC dimension exactly in n to the order of log n time. Furthermore, there is also a trivial algorithm that runs in polynomial time and give a log n approximation. Essentially, we can just output 1 on any non-trivial concept class. We can also get a trade-off between the two if we use some sort of limited brute force, where if we run in n to the p time, we can get some log n divided by p approximation algorithm. So why are these interesting? One of the more interesting things here is that since we have an n to the order of log n time exact algorithm for these problems, they are unlikely to be NP-hard, as otherwise all the NP-complete problems will be solvable in quasi-polynomial time. This means that to prove hardness for these problems, we need stronger complexity assumptions than just p not equals to np. One complexity assumption we will be using is the exponential time hypothesis, or ETH, which states that no 2 to the little o of n time algorithm can solve 3-stat exactly, where n denotes the number of variables. We will also be using a strengthening of this hypothesis called gap ETH, which says that in the same running time, no algorithm can even distinguish between a satisfiable 3-stat formula and one that is not 99% satisfiable. We will also be using complexity assumptions based on the planted clique problem. So let's recall that problem quickly here. There are two distributions of interest here. The first is Gn.5, which is just the uniform distribution over all n vertex graphs. The second distribution is the one where we first draw G from Gn.5, and then on top of it, randomly plan a clique of size k. The goal of the planted clique problem is then to distinguish between these two cases. So for the planted clique problem, there is a trivial n to the order of log n time algorithm. This is because in the Gn.5 case, the maximum clique size is at most order of log n. So we can enumerate through all the clique of size order of log n. If we find one, then we know that we are in the second case. Furthermore, when k is large enough, in particular if k is order of square root n, then the problem becomes solvable in polynomial time using spectral method. The planted clique hypothesis, or PCH, states that this spectral algorithm is essentially the best possible in the sense that if k is little o of square root n, then the planted clique problem is not solvable in polynomial time. Recently, there is also an extension of this hypothesis called the strong-ish planted clique hypothesis, or SPCH, which states that if k is polynomial, a small polynomial in n, then planted clique is not solvable in n to the little o of log n time, which means that essentially the brute force algorithm is the best possible that we can do in that case. Okay, so these are the 4 complexity assumptions that we'll be using in this work. Let us now state the previous result and then our results. The first result on this problem was proven by Pavdimitu and Yannakakis in 1993. They showed that computing VC dimension exactly is complete for the class called lognp. We will not be using this class here, so I will not define it, but it is essentially a limited non-determinism version of NP that corresponds to this n to the log n time algorithms. A few years later, Frances and Littman show that computing Littlestone dimension exactly is log NP hard, although they did not show that this problem is contained in log NP. A consequence here is that if we assume the exponential time hypothesis, then there is no n to the little o of log n time algorithm for computing the VC dimension or Littlestone's dimension exactly. In other words, the brute force algorithm that we discussed earlier in this talk is the best possible for exactly computing these dimensions. These hardness results have been extended recently by myself and Aviat to approximation algorithms. In particular, we show, assuming ETH, that there is no n to the little o tilde of log n time algorithm that can approximate VC dimension to within any factor less than 2. For Littlestone's dimension, we get a slightly weaker result where the inapproximability ratio is only slightly larger than 1. While these are good initial inapproximability results, they still leave quite a few problems open. For example, there could still be a polynomial time constant factor approximation for VC dimension or Littlestone's dimension. In this work, we provide several new inapproximability results that rule out such approximation algorithm. For example, assuming gap ETH or strongish planted clique hypothesis, we can show that no polynomial time algorithm can get little o of log n approximation for VC dimension or Littlestone's dimension. And this approximation ratio is tight because recalling from earlier that there is a trivial polynomial time log n approximation algorithm for both dimensions. While this result only rule out polynomial time algorithm, we also provide results that get the tight running time lower bound as well. In particular, assuming the strongish planted clique hypothesis, we can show that no n to the little o of log n time algorithm can get constant factor approximation for these dimensions. Finally, we also have quite a few additional results that are in between these two results. For example, for gap ETH, instead of getting the tight running time low bound of n to the little of log n, we only get n to the little of log n to the 1/3. There are many more results of this form that are not completely tight, but I will not be stating them here. All right, so those are the quick summary of our results. Let me now discuss how we prove these results. And as the title of our paper suggests, we are proving this result via a reduction from the Biclique problem. So in the Biclique problem, we are given a bipartite graph and an integer k. The goal is to determine whether there is a Biclique or complete bipartite graph that has k vertices from the A side and k vertices from the B side. For example, if this is our input bipartite graph and our k is equals to 2, then we may pick these last two vertices for A and these last two vertices for B, and they would induce this balanced Biclique. It would be convenient also to consider the gap version of Biclique when stating the hardness results. In particular, in the gap version, we want to distinguish between the yes case, where the graph G contains a Biclique of size k1, and in the no case, the graph G doesn't contain even a Biclique of size k2, where k2 is much less than k1. As the title of this talk suggests, we are not actually going to be using this balanced version of Biclique problem directly. Instead, we will be using what we call the exponential Biclique problem. So the setting is exactly the same as before, except that while we are still asking for k vertices on the B side, we are now asking for 2 to the k vertices on the A side. Like for example, if k is equals to 2 here, then we would want to output 4 vertices on the A side and just 2 vertices on the B side. Again, we can define the gap version of this exponential Biclique correspondingly, where in the yes case, we should have this 2 to the k1 and k1 Biclique. And in the no case, the input graph doesn't even contain 2 to the k2 and k2 Biclique. So let us note here that there is a trivial reduction from Biclique to the exponential Biclique problem, which we will be using. In particular, if we have the gap Biclique hardness, where in the yes case, the graph G contains 2 to the k1 size balanced Biclique, and in the no case, it doesn't even contain k2 Biclique, then this immediately implies the k1, k2 gap exponential Biclique problem by just keeping the same graph. And this follows immediately from the definition. Note, however, that we will need a pretty large gap in the original gap Biclique problem. So this brings us next to the main reduction. Our main reduction in this paper is a reduction from the gap exponential Biclique problem to the problem that we call gap VC dimension and Littlestone dimension, which is stated as follows. So we are given a concept class C, and we want to distinguish between the yes case, where the VC dimension of the input class C is at least D1, and the no case, where the Littlestone dimension is less than D2. And here again, D1 is a parameter that is larger than D2. Now recall here that the Littlestone dimension is always at least the VC dimension. This means that a hardness of this D1, D2 gap VC Littlestone dimension problem immediately imply hardness for approximating for both the VC dimension and the Littlestone dimension at once. In particular, if we can prove the hardness of this gap problem, then there can be no D1 over D2 approximation algorithm for these dimensions. This is another interesting aspect of our work because our work requires just a single reduction, whereas in the previous work, there has to be separate reductions for VC dimension and Littlestone dimensions. In terms of the exact parameter, we can get the yes case in our VC and Littlestone dimension to have dimension at least k1 over 2, and the no case to have Littlestone dimension less than 2 times k2, where k1 and k2 are the parameters from the gap exponential Biclique. So this gives a hardness of approximation for VC dimension and Littlestone dimension of approximation ratio k1 over 4 times k2. So in other words, we only lose a factor of 4 in the hardness of approximation from this reduction from the gap exponential Biclique problem. With the main reduction in mind, let me now quickly describe the overall framework that we use to get all the different hardness results that I have stated earlier in this talk. So many previous papers have already studied the balanced version of Biclique. And even though here we require the gap to be quite large, where in the yes case, it has to be exponentially larger than the no case, it turns out that many of these results still apply for such a large gap. So we can get the hardness for gap balanced Biclique directly. And then using the trivial reduction we talked about a couple slides ago, we can go from this to a hardness for gap exponential Biclique. And then we apply our main reduction, which then gives the hardness for approximating VC dimension or Littlestone dimension. This is the entire framework. So while I will not be stating all the instantiations of this result and all of its parameter, let me show you one example just to get a feeling of how such a framework can be applied. In particular, in this example, we start from Chalermsuk et al. Result, which say that assuming gap ETH, there is no polynomial time algorithm for gap Biclique, where in the yes case, there is a biclique of size n to the little of 1, and in the no case, there is a biclique of size omega 1. So using the trivial reduction we discussed earlier, we get a hardness of gap biclique, where in the yes case, the k1 is little of log n and k2 is omega of 1. So from this, we apply the main reduction. So we get that the gap we see Littlestone dimension is also hard for polynomial time algorithm, where the yes case, the d1 is little of log n, and in the no case, the d2 is omega of 1. And that's it. This immediately gives us that assuming gap ETH, there is no polynomial time algorithm that gives little of log n approximation algorithm for VC dimension or Littlestone dimension, which is our tight inapproximability hardness result. With that example done, we'll now get back to our main reduction and see how it works. Let us start with a simple attempt, and this is perhaps the most natural reduction there is, which is just to take the concept class to be the adjacency metric of the input graph G for the exponential biclique problem. For example, if this is our input graph G, then we just write down its adjacency metric, and this is our concept class. Note here that now each vertex from the side A now becomes a concept, whereas each vertex on the side B becomes a domain element. So let's see whether this reduction works. And let's start with the soundness of the reduction. To do this, let's recall very quickly the halving algorithm. Recall that this is the algorithm where we keep a set of candidate concepts that agree with all the examples so far. And we try to predict in such a way that if we are wrong, then at least half of the candidate concepts will be ruled out. And this gives the bound of log of the concept size on the mistake bound. Okay, with that in mind, how do we use this halving algorithm to prove the soundness of this reduction? Just to quickly recall, in the soundness proof, the goal here is to show that if the input graph G doesn't contain 2 to the k2 k2 biclique, then the Littlestone dimension of the resulting concept class should be less than 2 times k2. So to show that the Littlestone dimension is small, it suffices to give a learning algorithm with small mistake bound. So how does our learning algorithm work? The learning algorithm works in 2 phases. In the first phase, we will always predict 0. We keep doing this until we make k2 mistakes. Once we make k2 mistake, we switch to use the halving algorithm that we just discussed. Now, how can we analyze the mistake bound of this algorithm? Obviously, if we never reach the second stage, it means that we make less than k2 mistakes. So we are done already. So we only have to consider the case where we reach the second stage, which means that we make k2 mistakes in the first stage. So if we make k2 mistakes in this first stage, what does it tell us? So let's think about this for a moment. If we make k2 mistakes in the first stage, since we always predict 0, it means that the true concept class has to predict 1. So what this means is that if we take a look at the graph induced by the set of the remaining candidates and the elements that we make mistakes on in the first stage, then it must induce a biclique. And since we assume that there is no 2 to the k2 and k2 biclique, and we already make k2 mistakes, meaning that there are already k2 elements on the side B in the mistake set, then we have that the candidate set must be of size less than 2 to the k2. In other words, once we reach the second stage, the candidate set that we are left with has size less than 2 to the k2. But this means that since we are using the halving algorithm, we will be making at most K2 mistakes in the second stage. So in total, the number of mistakes that we make is less than 2 times K2. And that's it. That's the entire soundness proof. So far, so good. How about the completeness? So what do we want to prove again in the completeness? We want to show that if G contains a large Biclique, a 2 to the K1 Biclique, then the VC dimension of the resulting concept class C has to be at least K1. Unfortunately, as you might have noticed, this is actually not true. A simple counterexample here is when G is the complete bipartite graph. In this case, the resulting metric C is the all-one metric, so its VC dimension is just 0. Now, the issue here seems to be that there are, in some sense, too many ones in the metric C. So how do we fix this? So in the final reduction, instead of taking the adjacency metric of the graph G directly, we start by first removing each edge of G randomly with probability 0.5 independently. And then after that, we then take C to be the adjacency metric of this modified graph. It turns out that the soundness proof goes exactly as before. And in the completeness proof, it's also not hard to argue that with high probability, the VC dimension of the resulting class is now large, at least K1/2. So that's it. That's the final reduction, very simple. And that's also all the high-level ideas of the proof. So with that, let me conclude here. We provide several new hardness or approximation results for VC dimension and Littlestone's dimension. For example, we can get the tight approximation ratio. Assuming gap ETH or strong-ish Biclique hypothesis, we rule out little of log n approximation algorithm in polynomial time. We can also get tight running time lower bound. For example, we rule out, assuming strong-ish Biclique hypothesis, any constant factor approximation algorithm in n to the little of log n time. And we also provide many other results in between these two as well. Nonetheless, there are still quite a few open problems. Recall that the VC dimension itself is log NP complete, while the Littlestone dimension is log NP hard. So one might wonder whether it's possible whether we can prove log NP hardness or approximation for these results, and that remains an interesting open problem. Another problem that I sort of touched upon a little bit earlier is that the Littlestone dimension is not known to be contained in the class log NP. So it would be interesting to show such a containment or define a new class or identify a new class for which Littlestone's dimension is complete for. All right, and that's it for this talk. Thank you all very much for your attention. Thank you.